Hello everyone, my name is Ruben Mascaro and I am with the Vision for Robotics Lab at ETH Zurich. In this video, I will introduce our work on domain adaptive semantic segmentation with memory-efficient cross-domain transformers. Annotating application-specific datasets to train semantic segmentation models is extremely costly. A promising alternative is to leverage related but more accessible domains such as synthetic data and transfer knowledge to the target domain without requiring target labels. This problem is known as unsupervised domain adaptation, or UDA in short. Modern UDA frameworks typically build upon the self-training paradigm, where the model is trained with ground truth labels for source images and pseudo-labels for target images. The pseudo-labels are generated by a teacher network, which is the exponential moving average of the student. Recently, with DA-Former, transformer architectures were shown to boost UDA performance compared to previously employed convolutional neural networks. However, even these more powerful models struggle to effectively learn context relationships in the target domain. This typically leads to the confusion of classes that have similar appearance, such as road and sidewalk in these examples. To address this issue, we exploit the transformer architecture for better source-target feature alignment. Specifically, besides the commonly employed source and target branches, we add an intermediate branch that takes the target image as input and then computes features by fusing the output of intra and cross-domain attention. This way, the network learns to use relevant context clues from the source domain to segment images in the target domain. Our architecture can be easily used within self-training UDA pipelines by adding an extra loss to enforce consistency between the predictions of the cross-domain branch and the pseudo-labels. To test our approach, in this work we use the DA-Former UDA framework as baseline. First, we run experiments on popular synthetic to real UDA benchmarks. On GTA to cityscapes, for example, we see that our method improves the ability of the model to distinguish visually similar classes, such as sidewalk and road, or terrain and vegetation. We also evaluate our approach on the cityscapes to AC/DC benchmark, where the goal is to adapt from clear to adverse weather conditions. In this case, the improvement of our approach over DA-Former is even more significant. For instance, we can see that our method does a better job at distinguishing between road and sky, achieves better segmentation for walls, and is also less prone to predict wrong labels on parts of vehicles, such as buses or trains. Finally, we also provide a comparison against other cross-domain transformer architectures recently developed for UDA. For a fair evaluation, we integrate each of those in our UDA framework and run experiments on GTA to cityscapes. Results reported in the table below indicate that our approach achieves the best accuracy by a slight margin. However, a notable advantage of our method is that it does not increase GPU memory consumption compared to the baseline DA-Former, where only the source and the target branches are used. That's because, as opposed to the other architectures, our design does not require gradient bump propagation through multiple branches at the same time, allowing each branch to be trained separately. This leads to significantly faster and cheaper training sessions. For more details, please check our paper and our implementation, which is available on GitHub. Thank you for watching.